All right. Well, hello, everybody, and welcome to our May 2023 Akka.NET Community Stand-Up. My name is Aaron Standard, and I'm joined here by Gregorius Sodharmo, who's on the Petabridge team with me. Gregorius, how are you doing today?
Oh, pretty good. Thank you. And how are you?
Doing all right. Made it back just in time for my coffee run to go ahead and start our community stand-up here. Got it kind of down to the wire, but that's okay. In fact, I might bring my cappuccino over here. We're going to go ahead and kind of start from the bottom and work our way up in terms of the release notes here, because we actually shipped quite a number of things since our April meeting. So
Mhm.
first thing we'll go ahead and take a look at is Akka.NET 1.53. So Gregorius, I think this was your release primarily. If I can go ahead and
Yes.
get the recent Akka.NET releases banner up. There we go. All right, why don't you take us through this one real quick?
Yeah, this is quite a big update, actually. One of the minor one is we found a bug in the Hyperion serializer setup. It's not really applying its configuration correctly, but we fixed that. And the big change is that we added a separate transaction isolation level setting to both the read and write side of Persistence.Sql common. So this will affect all of the persistence plugins that are based on SQL servers, basically like Postgres, MySQL, Microsoft SQL servers. Uh, we found that on a very high write volume system, there's a race condition between two concurrent write transaction and a read that happens between the two writes. It doesn't really happen that often. I mean, the user that reported that the race condition happens once every 2 weeks or 3 weeks, I think, on a very high volume system. But we found that it happened on SQL Server, Microsoft SQL Server, and it happens because on some isolation level, there are no guarantee that a concurrent write are committed to disk in order. So if a read happens in between of those two transactions, one of them would be missing.
Yeah, this is an issue with it was the all events query I think they were having trouble with, right? Which
Yep.
uses an auto what's it called? Auto ID column. And there's no guarantee that there could be multiple auto IDs that are all sequential, but they all may not be committed in order. And so you can potentially miss some auto IDs. So we decided
Mhm.
as a simple fix for this to try to basically make the isolation level configurable. That way you can go ahead and basically probably lower the isolation level on reads and make sure that you can pick up those transactions that are in the process of being committed, even if they haven't yet. Which would
Mhm.
be necessary on a high write system. We've also discussed potentially doing like read behind as a way of trying to solve these types of problems on other non-SQL platforms. So we might be still doing some more work there yet, but that was kind of the gist of this. This was sort of a data consistency problem for Akka.Persistence query we were kind of trying to address. And I think
Mhm.
Gregorius' solution here is pretty straightforward. All the default isolation levels left as is. So by upgrading to this, you shouldn't notice any changes. But these settings are now exposed in Hocon and in Akka hosting if you want to change them.
Mhm.
Let's see. Next, this one was my release 1.54. Um, so I think Ishmael, if he's out there, will be happy with this. We finally made bounded stashes actually usable after, it's only been nearly 10 years, I guess. Bounded stashes has been something we've kind of theoretically supported in Akka.NET for a number of times. Basically, by default, most stashes that people use are what's called an unbounded stash, which means there's no capacity limit on the number of messages an actor can store that it isn't able to process at any given time. The only way to support bounded stashing was basically by doing a custom mailbox or something like that, which was, shall we say, a little bit cantankerous for most people. So one of the things that we did, well, we did two things here. First is we made it easy to go ahead and specify a bounded stash via props. Let's see here. I think I actually documented this on the Akka.NET website. Let me pull it up real quick. Go to documentation, actors, receive actor API, and I go to stash, bounded stashes. Here you go. We have two different ways of being able to specify to basically make a stash bounded now. So the actor just needs to implement the I with stash interface. And if you implement the interface, you can configure the stash by this little Fluent interface on prop. So I say with stash capacity equals 2, or I can do it via HOCON down here. I can say stash capacity equals blah if I wanted to. So that'll enable us to go ahead and make the stash change from being bounded to unbounded. On top of that, we also added these APIs to the stash right here, which basically allow you to check what the stash's capacity is, whether or not it's full, whether it's what its current, let's see what its capacity is, how much of it's actually used, and whether or not it's empty. So you can actually check all those properties now. We ended up using those in the feature that I'm going to be talking about during our show and tell presentation today. Let's see. Next on our to-do list was Akka.NET 1.55. In fact, we've even released an Akka.NET 1.56, actually. So I only prepared these notes on Monday. We've actually done another release of Akka.NET since then. Let's see. Gregorius, this was basically, if I recall correctly, a whole bunch of various bug fixes. So we fixed receive async receive timeout issue, where basically if you're using receive timeout plus receive async, you never got a receive timeout. That's been fixed. And then on top of that, we fixed a whole bunch of byte string issues. Basically, the byte string construct in Akka.io would allow you to pull random garbage out of it, regardless of what values you passed in. Whoever originally designed it basically didn't put any bounds checking at all on there. So we added that. Fixed a race condition with fast lazy. That's kind of used all throughout Akka.NET. We made it so Akka.F# now properly works with .NET 6. That I won't get into the details on that. Then on top of that, you added a new overload to expect all that accepts predicates, and it has to satisfy what one or only has to satisfy what one of those predicates in order to work.
It's not mine actually. It's
that's right. That
else.
was Malcolm's thing. Well,
yeah.
Anyway, I don't expect that feature to get used all that heavily, but the developers who are working on the Akka.Texture project, which is popular for doing CQRS with Akka.Persistence, uses that. So we just kind of added that to support them. Lastly, a small but important change for production users. Gregorius, this is your doing here. We basically changed the date time format in our logs to a 24-hour format instead of 12, right?
Yep.
So this should make any log aggregation you're trying to do based on the time of day much easier to understand now. I think it was driving some people nuts before. I think we changed it from 24 to 12 and Akka.NET 1.5 by accident because we were fixing a couple of other issues of the time format at the time. But now I think we're on an even keel with all this stuff, right?
Yes. Well, the problem is, of course, Microsoft way of specifying date formats. We missed small h with capital H, which differs between 12 and 24-hour format.
Yeah, if I go take a look at the diff here. Yep, that's what did it. Whoops. Now we know.
Yep.
Okay, let's see. Petabridge.Command 1.31. This was a fun one. Basically, a user reported in Discord that Petabridge.Command.Host was causing their process to run out of memory whenever they had a scheduled security scan run behind the scenes. Well, it turned out that scheduled security scan was basically bombarding the Petabridge.Command.Host port with random SSH messages, which don't use the same frame length encoding that Petabridge.Command does. And as a result of that, plus those byte string errors we talked about, where byte string never validated its input, this could basically continuously consume memory. So we've added some sanity checking to Petabridge.Command's decoder. It kind of matches what Akka.Remote does to some extent. Where we basically say, look, if we pull a super large or a super small, like negative value out of our length decoder, we're just going to throw them at, we're just going to crash the connection and force it to reopen. That way we don't end up running out of memory and crashing someone's process. So that's kind of built in there. Phobos 2.3. I'm going to do a blog post about this, but in lieu of that, maybe you should go ahead and discuss this real quick, Gregorius.
Okay. Well, the big change is that we updated all of our OpenTelemetry plugins to 1.4.0, which includes an update for OpenTelemetry extension hosting which was beta before this. So there are a lot of API changes, but we actually updated all of our samples to use the new API. So you can actually just refer to that if you need to make any changes.
So yeah, basically to give you a little bit of inside baseball on this, the Open Telemetry project screwed up. They released a whole bunch of stable stuff around 1.3, said it was stable, and then changed their mind when it came somewhere midway through. And so they completely changed their hosting APIs. They moved some of their exporter functionality into different packages. So, for instance, Prometheus is now split up into two different packages. And then on top of that, I think they changed some of their BCL dependencies. Most of this stuff is going to be invisible, but the hosting stuff, unfortunately, is not, which is the way you configure Open Telemetry. So
Hmm.
all they really did was they kind of went from having two separate methods to one unified method with two builders. So it is not an earth-shattering change, but it is absolutely a breaking API compatibility change. Don't know why those guys did it that way, but it is what it is. We've updated Phobos to go ahead and support that. So, okay, 1.4 is supposed to be kind of the mature, stable version of this going forward. We'll see if Open Telemetry keeps their promise this time, but we're just taking them at their word for it. And that's sort of what this covers. If you're an existing Phobos user already, we do have a page that kind of walks you through the upgrade process for this, which is all about basically here's what's new in the versions of Open Telemetry, and here's what your configuration used to look like, and here's what it's going to look like now. So we kind of cover all the different little upgrade steps there. Last thing I guess we'll discuss real quickly is the Akka.net 2023 Developer Survey is out now. I think we've probably had close to 100 responses so far. I haven't checked the most recent total. Usually we look for 200 to 300. So we're going to keep promoting this over the course of May. And my guess is in our June community stand-up, we'll go over the results. Uh, Basically, the developer survey or slash user survey, we kind of use those names interchangeably, is really important for us actually because it's what we use to kind of determine what we should be putting on our product roadmap. So, for instance, an example of a couple of things that have come out of the survey in years past. For starters, Akka hosting definitely came out of it. We saw in our survey feedback, let's say in 2021, for instance, a lot of people wanting Microsoft.extensions integration. Well, so we delivered, I think, an early prototype of Akka hosting in maybe like April of 2022. And actually, so I guess it might have been the 2022 survey that drove that home. But we picked that up from there. Petabridge.Command also came out of surveys back in like the 2016, 17 era. So that came out of that as well. Then also other tools like Akka Management. Akka Management existed obviously in the JVM ecosystem, but really it was people complaining about how much they hated Lighthouse that kind of motivated us to help start prioritizing it. So we do listen to your feedback on this stuff. We've gotten a lot of feedback about needing new documentation and tutorials as well. We will absolutely be doing that later this year. We have to do that anyway in order to incorporate some of the new Akka.net 1.5 stuff into our literature, namely Akka hosting in particular. So we are going to be doing a lot of that over the course of this year. But that being said, if you haven't taken the survey, you can go. I'll maybe drop a link to this in Discord. You can take it there. On top of that, we'll probably be sending out some more emails to the Petabridge mailing list about it as well. And we'll also promote it on our social media. So you can take it any one of those places. So I think that'll do it for our existing releases so far. Let's talk about the new stuff we're cooking up. All right. Gregorius, do you want to give a quick update on Akka.Persistence.Sql and let people know how that's going?
Yeah, it's close to being RTM. We are planning on moving out of beta on it. We are still waiting for inputs, like if people are actually using it. I knew that some people are actually trying it. There are some people who commented on it in Discord, but I guess we need to take their inputs into consideration
Yep.
to make it like easier to use.
Absolutely. So one thing that we've done recently with Akka.Persistence.Sql is previously we were encouraging people only to look at it for greenfield projects. Now we're encouraging people who have been using Akka.Persistence.Postgres or Akka.Persistence.Sql server, really any ADO.NET capable database to start taking a look at it. I'm actually using it in my demo app today, the for our deliverability feature. I think it works really well. It is noticeably quite snappy, so it's very fast. We do have a migration guide available here that kind of explains how to do it. I guess I'll probably blast this out on our Discord and our social media some. But basically, we're probably going to close the window for feedback on this library pretty soon, which means that the schema gets frozen, the API gets frozen, and anything you do or don't like about how it currently works is stuff that we're going to have to live with and maybe gradually version away if there's a problem down the road. But for the time being, it's still open for feedback, still in a bit of a beta state. I would definitely encourage you to take a look at it. I don't know if hyperlinks work when I post them in StreamYard. I don't think they do. No, they don't. But you can, I just tried it just now. But here's the migration guide. You can take a look at this. This will be coming out probably by the end of the month, to be my guess.
Mhm.
Next thing we'll talk about is the subject of today's show and tell presentation. I'll go ahead and give you a quick preview here. This is a feature I've put probably about 100 hours into over the past 3 or 4 weeks. It's originally from the Scala version of Akka. It's called Akka.Delivery. I ported it from the 2.6.19 version of Scala, which is still licensed under Apache 2. So that should all be fine. And we're going to go ahead and dive into how that works in our show and tell presentation, which I will begin right now. So let me go ahead and just change our layout real quick and get PowerPoint up and running. All righty, got that. And let me go ahead and flip to this real quick. Okay. Introduction to Akka.Delivery. What is this for and what are we doing with it? Well, the first thing we'll talk a little bit about is how does message delivery work in Akka.NET today, right now, and what are some of the things you can do to try to make Akka.NET's default delivery a little bit more robust as of this morning. And then we'll talk about the future, Akka.Delivery and also Akka.Cluster.Sharding.Delivery as well. We'll go ahead and see examples of both of those in the next couple of minutes here. So there's 3 fundamental models of message deliverability in distributed systems. There's at most once delivery, also known as fire and forget messaging. This is Akka.NET's default. We use at most once delivery. Then there's at least once delivery, where the sender has to keep track of messages that are in flight, and any messages that are not explicitly acknowledged by the receiver are going to be redelivered. Messages might be duplicated, and it's also possible in an at least one scenario that messages might be delivered out of order. And then finally, we have exactly once messaging, which is what everybody ideally wants. However, the issue with exactly once delivery is that both the sender and the receiver must maintain state. They need to be able to keep track of what messages have been previously processed and which messages have been acknowledged. This also might require slowing the sender down and forcing it to only redeliver the message at the front of its delivery queue in a given time. In fact, this is actually how our Akka.Delivery system generally works here. So exactly once delivery basically is at least once delivery with deduplication built into it. Now, the reason why Akka.NET does not use anything stronger than at most once delivery by default, well, we use at most once delivery because it's stateless. For a system like Akka.NET, where there might be tens of millions of actors all running inside the same process, keeping track of message deliverability state all over the place would get expensive really quickly. You would see big surges in memory consumption, and not to mention redeliverability, memory pressure, CPU pressure, all sorts of stuff if we did this. So we go with the sort of least expensive option here. On top of that, at most once delivery is also the fastest because it's unidirectional communication. The sender delivers a message to the consumer, and then the sender promptly forgets about it. So that's why we do that. And then for in-memory processing, let's say you're not building a distributed system with Akka.NET. Let's say everything's all running inside one process and it's all in-memory actors talking to each other. You generally don't need anything more robust than one-way messaging at most once delivery in those environments, because the only way a message can get lost would be if the consumer crashed or got killed in the middle of processing. In which case, you can probably handle that really easily in a application-specific context if you needed to. So at most once delivery is generally good enough for most use cases. However, where it's not good enough is in instances where you're sending messages over the network and you're potentially vulnerable to message loss as a result of network partitions, or possibly as a result of things like actors being rebalanced in Akka.Cluster sharding, or maybe as a result of something like a process termination. On top of that, yes, we are, even in an in-memory scenario, we also are vulnerable to message loss in restart scenarios where actors restart. So that's kind of one half of the Akka.NET defaults, is the message deliverability guarantees. The other problem I want to address has to do with how we serialize and transmit messages over the network. I wrote a blog post, actually it might have been Andrew who wrote it back in 2015, about large messages going over Akka.remote. This has been somewhat of a problem we've had since the very beginning of Akka.remote, which is that the way Akka.remote works is you have actor system A, actor system B, and they are communicating with each other via a duplex TCP socket. So you have messages going in, messages going out on both ends here. The way Akka.NET serialization works is we take your user-defined message, we use one of our serializers or possibly a user-defined one to turn that message into a byte array. That byte array then gets what's called length frame encoded, which means we append a little 4-byte header that describes how big this message is. And that gets lumped into the same byte stream as all the other messages that appear inside your message traffic. So this is what that byte stream might look like. TCP preserves message order and it guarantees delivery of all packets so long as the connection doesn't get severed. So what you might see if I laid out that TCP byte stream as a contiguous sort of flat byte array is, from the point of view of the end user's application, this just looks like one big array of bytes. However, what our encoding process does is it says, okay, I know, let's say that there's going to be a 1-byte header here, and that's going to describe how big this message can be. So 1-byte header, 4 bytes of content. This might have a 1-byte header with 5 bytes of content, 1-byte header, 3 bytes of content. We discard the headers and then we take the content and then we deserialize it and turn it back into the C# and F# messages your application's used to working with. And so this is what we call interleaving of messages when this happens. It means that multiple messages are all being written to the byte array at a given time. So when we do a read from our socket, we might actually pull multiple messages out of it all at once. This also importantly includes, we might pull a partial message out, meaning that if you have a fairly large message, we may not pull all of the bytes out all at once. We might only get a fraction of it, in which case we got to save that chunk and then combine it again. Akka.remote's network layer handles this for you. What Akka.remote's network layer does not handle is what we refer to as head-of-line blocking. This is what happens when you try to flush an extremely large message over Akka.remote's transport. And basically what this does is that message can't really be interleaved by Akka.remote today. So as a result of that, that is going to hog the entire byte array. And any other messages, including time-sensitive ones like heartbeats, have to get queued up behind it inside the sender's application memory. We have to wait until that system memory that holds the outbound sort of socket buffer, it has enough room for us to add additional messages to it. And even then, we're a little bit limited by how quickly the reader can read on the other end of the network. So this is kind of a traffic management problem that Akka.remote is susceptible today because it uses only a single TCP connection. In Akka.NET 1.6, which we're talking about starting on, basically in fall of this year, we're going to move to a multiplexed UDP system, which isn't vulnerable to this type of traffic issue anymore. But for the time being, the system that we have right now does have this issue. So really large messages have a difficult time getting delivered currently. And when I say a really large message, in Akka.remote parlance, this is something, let's say 10 megabytes or bigger. Messages that are smaller than that, you can just increase your Akka.remote buffer and max frame sizes. Right? I think right now they default to largest possible message size is 128K. And the buffer sizes are 256K per read and per write. So 512 kilobits of memory per socket, basically per connection. You can scale those up. You could scale them up to, let's say, a maximum frame size of even like 3 or 4 megabytes and double that for your socket sizes, and that would be just fine. However, once you start getting into, let's say, 10, 100, 1 gigabyte size messages, Akka.remote's current delivery system just won't scale very well with that, because of head-of-line blocking, or as I call it, putting a pig through the snake, just like this little image shows here. So these are a couple of the problems that Akka.net's messaging system has today: a fairly weak delivery guarantee and also being susceptible to head of line blocking. We're going to try to address both of these issues with Akka.Delivery. Now, if you're not using Akka Delivery, which no one is because it's not released yet, but it will be very shortly, what are the other alternatives for doing message delivery today? Well, one possibility is you might use Akka.Persistence and the at least once delivery actor. And this is a diagram from our design patterns training that we teach. And nope, sorry, this is our Akka.Remote training is where we use this, where we have a message that comes in. The at least once delivery actor assigns that message a sequence number. That message gets delivered to a local actor who then tries to deliver over the network. And if that message doesn't get successfully delivered, this actor basically has a little bit of a dead man's switch where it can check to say, you know what, this message should have been acknowledged by now. And since it hasn't, I'm going to go ahead and requeue it for delivery. And then on the happy path, we basically send a confirmation message back that includes that sequence number, and the actor marks it as delivered. You, as the end user, are responsible for defining message types that store, oops, sorry about that. Defining message types that store the message ID number and pass back the confirmation number and handling both of these. And this is sort of what the code kind of looks like for an at least once delivery actor. It is a persistent actor, so it does need a persistence ID. I have to go ahead and recover my at least once delivery snapshot, and then I call set delivery snapshot on that. And then when I'm actually processing messages, I see, is this a message I want to reliably deliver? If it is, I have to pass in the actor path of the actor I want to send it to, which means if this is a remote actor, it's very possible that this process might die and never get created again, in which case none of these messages could get reliably delivered anymore. They essentially go across a bridge to nowhere when that happens. And then if I get my message confirmation here, I can call confirm delivery. And then otherwise, every time I process a message, I have to save a new snapshot. This is because the at least once delivery actor, for trying to, let's say, persist its delivery state, which it does not do by default, if you do want to persist it, you have to do it by saving and overwriting snapshots constantly, which is a tremendous pain in the butt to do correctly. So yeah, the other problem is that it's very difficult for receivers to perform duplicate detection. We have a library that I developed 4 or 5 years ago called Akka.Persistence Extras, which has a actor called a persistence supervisor. That persistence supervisor tries to perform duplicate detection and buffering while a consumer restarts. And it's actually very similar to how the consumer controller works in Akka.Delivery, which we're going to be covering in a minute. So it's inconvenient to do duplicate detection. The original message order is not preserved. The at least once delivery actor is hilariously bad at preserving message order, actually. It operates off of a very flimsy sort of timing mechanism. It doesn't really respect the original delivery order and honestly has no real concept of how to preserve it either. It all just kind of looks like a queue with some messages that need to be delivered and others that don't. And it kind of arbitrarily schedules them for redelivery. Then on top of that, the persistence model is not good, only uses snapshots. And it's also easy to accidentally render all queued messages as undeliverable if you're persisting, let's say, a remote address. So typically, in order to even use the at least once delivery actor correctly, you usually need to have a second actor that you design that does something like Akka.Cluster routing or something, where basically it uses a separate actor for figuring out who can actually process this message in the event that the original recipient gets moved or killed. The other technique people can use for reliable delivery today, in fact, we have a code sample that kind of demonstrates this, is an external technology like RabbitMQ or Apache Kafka or Azure Event Hubs. Now, there's nothing wrong with doing this. In fact, we see this pattern quite often in practice where a developer will go ahead and integrate Akka.net with like a big Rabbit system they've had in place for years. Akka.net and these other technologies work very well in concert with each other. But if you're introducing these exclusively for the purpose of trying to facilitate reliable delivery inside Akka.net, it's going to introduce a ton of extra infrastructure, monitoring, and deployment that you don't have. And on top of that, it's going to introduce an additional layer of serialization and indirection inside your system. In other words, while there's nothing wrong with these technologies, it's simply just expensive. On top of that, none of these technologies really address the head of line blocking issue. If I try to flush a 100 megabyte message on RabbitMQ or Kafka, that may not work very well either. So there's a number of different issues that kind of remain unsolved here. So what we're trying to shoot for with Akka.Delivery. And yes, these typically have a higher latency than Akka.net as well. What we were trying to shoot for with Akka.Delivery is something that is a first-party solution that is relatively simple for developers to implement that kind of addresses both of these key deliverability problems. Namely, we need a way to make sure that we can efficiently deliver messages inside Akka.net without relying on external infrastructure. We need the ability to potentially survive process restarts, and we also want the ability to preserve message order and deduplicate messages if necessary. And this is what Akka.Delivery was built to do. Basically, Akka.Delivery has kind of two different modes built into it. There's point-to-point delivery, which is reliable and optionally durable. This kind of works very similarly to how the at least once delivery actor was meant to work in theory. This preserves message order, so messages will be redelivered in the original order in which they were sent. The other thing that's interesting about this is our first time kind of experimenting with strongly typed messaging protocols. Akka.Delivery was ported from Akka typed. We don't have typed actor references yet, so that's kind of one little point of friction that this API might have. But the actual message protocols and the actors themselves are all strongly typed. So that's something that we've implemented. On top of that, we also support back pressure for Akka.Delivery. In other words, we have a way of signaling to the producer that the consumer either hasn't been relocated yet or isn't processing messages right now or is busy, in which case it's up to the producer to decide how it wants to handle that. And the producer is your user-defined actor. And this is all implemented via kind of a simple messaging protocol. The other key feature that Akka.Delivery supports is chunking for large messages. The ability to take, let's say, if I take a message and I serialize it and it's 5 megabytes and my maximum frame size is 128 kilobits, I can go ahead and say, you know what? I want to go ahead and chunk that 5 megabyte message into 128 kilobit slices and deliver them over the wire. This basically allows us to sort of safely transmit that message while not also blocking all other traffic going over the connection. This will ultimately make your systems much more reliable. There'll be a slight latency penalty for using it, but the alternative is having, let's say, unpredictable network outages and other issues like that. So Akka.Delivery will help a great deal with chunking support. Now, there is another mode for Akka.Delivery that we decided not to implement in this past, which is a pull-based delivery. This is kind of what it's like reading from, let's say, Akka.Persistence.Query, or maybe reading from Kafka, where you have a consumer that kind of works its way through the producer's partition. We will probably not implement pull-based delivery for some time. We'll stick with the point-to-point stuff for now because that's what's supported in cluster sharding, which is sort of what we built this feature for. But for other developers who do want to use pull-based delivery, we might consider making that available in the future as well. We do have an open action item for it. So to get started here, here's kind of what the stage looks like for Akka.Delivery. We have 4 actors that all play a part here. A producer and a consumer. These are your application-specific user-defined actors. Your producer gets its messages however it does. In the case of our demo we're going to show for this today, its messages come in the form of HTTP requests from a web UI, Razor page specifically. This producer, sorry about that. That's actually the consumer actually sends consumption requests that way, is how we're doing it. So we actually kind of have it engineered a little backwards here. So the consumer basically gets a request from a web API. It'll send a message over to the producer, and that producer will go ahead and basically fire a message off into the producer controller that will reliably deliver it over the network and close the loop here. The producer controller and the consumer controller are what we built. They are part of Akka.net now, and they ship in the core Akka DLL. They'll be available as part of 1.5.7. We will probably do a beta release of that library later today so you can get access to it. Now, what does the producer controller do? This is where most of the actual function comes for Akka.Delivery. So it happens inside this class. It has a unique producer ID. This is one of the ways we can kind of identify from on the consumer side where messages are coming from. And this is really important from a deduplication standpoint. If you ever used Akka.Persistence extras, we use the at least once delivery actor's persistence ID to do this job there. The producer controller automatically sequences all messages, so it assigns every message a monotonically increasing sequence number and optionally chunks those messages into individual byte arrays. And chunks also get sequenced as well. They all get their own sequence number. and they get delivered. All the producer controller basically gets all of its input from your actor, the producer. The producer controller is designed to work with a consumer controller. The consumer controller can be in memory, but it's really meant to be kind of over the network, is what it's for. And it works to make sure that there aren't too many messages outstanding that haven't been processed by the consumer yet. Once we start butting up against that limit, we're going to go ahead and essentially stop telling the producer that we're ready for additional messages. We're going to it's kind of works similarly to Akka streams. We're going to stop sending demand for new messages, and the producer should react to that by essentially buffering or slowing itself down or pausing message production. So that's what we do here. And then, so this is how we sort of back pressure the producer when buffers are full. And then finally, we also optionally support the ability to persist our delivery buffer and state. This means that we have the ability to essentially recover from a process crash if we need to, and re-deliver any unacknowledged messages. So that's something that we can do pretty easily with the producer controller. By default, you don't have to run it that way if you don't want to, if you don't want to make it persistent. Otherwise, the way we persist this delivery state is basically built on top of what's called a event source delivery queue. That's going to be part of the Akka.Persistence library, and that uses basically the Akka.Persistence journal and snapshot store to go ahead and keep track of delivery state. The consumer controller sits on the receiver side, and it's basically responsible for maintaining a sorted buffer of messages it's received from the producer controller. But if those messages haven't been acknowledged by the consumer yet, then the consumer controller considers that they really haven't been processed just yet. So we maintain this kind of sorted finite buffer of unacknowledged messages, and we keep track as the consumer processes them and acknowledges those messages back. We'll go ahead and tell the producer controller we're ready for additional messages right now. And as a result, the producer controller will begin requesting additional message flow from the producer. And this is kind of what keeps the system running this way. On top of that, in the event that, let's say, the consumer is running behind and hasn't processed a message within a finite window, we will redeliver that message to the consumer and get it to try to reprocess it if we can. On top of that, we might also re-request messages from the producer controller in the event that we haven't heard from it in a little while. So basically, there's a whole bunch of checks in place here that are all kind of designed to make sure that reliable message flow continues, whether or not there's intermittent pauses on the consumer or the producer side. So this is kind of what the little registration workflow looks like. In order for this system to get up and running, we've got to do three things. The first is that the consumer and the producer both need to respectively register with their controllers. They do that via a little start command. And you'll notice all of this is generically typed here. That's not an accident. You basically need to specify when you create a producer controller what types of messages the producer controller can handle. I'll show you in my concrete code sample in a minute how we do this. But basically, usually you should be organizing your messages that belong to a particular domain. You should be organizing them with an interface that basically says these all belong to this domain. And that's really what this type constraint should be right here. If you're not doing that today, you should start getting in the practice of it. It has a lot of other benefits aside from playing nicely with the producer consumer controllers. It's also a much easier way to kind of organize messages together for doing things like pure functions and processing or serialization and so forth. So that's kind of what we're doing here. The other thing we've got to do is we have to get the consumer controller registered with the producer controller, which we can do by either sending this consumer controller a register to producer controller message, or we can tell the producer controller to register this consumer. Either thing will work. But once all of this is done, the message flow can start. So what the message flow looks like in practice is when the producer controller is ready to basically stream some messages over the network, your user-defined actor will receive a request next message of type T. You should reply back to that request next message with a one message of type T up here. Go ahead and send that in. So one of these equals one of these. The sharding version of the producer controller will actually accept kind of a bigger buffer of messages potentially. But that being said, you will run into trouble if you exceed the buffer space that's inside of here. This system will actually crash and throw an exception and will force the entire redelivery process to start. So you want to be a little mindful about these request next messages coming in. I've been able to handle this with really simple behavior switching is all that I need to kind of do it. Where if I get input that I need to deliver and I haven't had a request next in a while, I'll use a stash, stick it in there, and then When I get a request next, I'll unstash it, send that message. And then as long as I keep getting requests next, I'll just go ahead and dequeue all of that into the buffer. So that's all we need to do to kind of make this work here. The producer controller will chunk the message optionally. I'll show chunking in just a second. And we'll route the message over the network to the consumer controller, who will then message this via a delivery T message. It's not job delivery, it's just delivery to this consumer actor here. When the consumer actor processes this message, it'll go and reply back to the consumer controller with a confirmed. The consumer controller will keep track, well, essentially will pop that message out of its buffer and say, okay, this message has been processed, we're good. It'll increase the sequence number of messages it's seen, and it'll go ahead and let the producer controller know that basically, hey, we're ready for more demand, in which case the producer controller will go and ask for it. And this is sort of the little workflow that keeps the system in motion here. Now, the next thing I'll show before I do my demo is how chunking of large messages works. This is how we solve the head of line blocking problem. So this is an example of how we create our producer controller inside the code sample I'm going to pull up, where I'm going to go, create some producer controller settings right here. And I'm going to say, these are all, by the way, this is another new thing we've done is we actually have support for record types and other new C# features now in Akka.NET, including in the .NET standard version of this. So this is a C# record that we're using to create the settings class. This is sort of a new thing that we started doing. And we're going to say, okay, I want to set my chunk large message bytes value to 64 by 1024. That's going to be 64K. Then I'm going to create my producer controller props. I'm going to pass in a little generic argument here that specifies the type of message this producer controller can handle. And this will also be reflected in the message types that this producer controller sends. And I'm going to create my producer controller right here. I'm going to register my consumer with it. And then I'm going to register my producer with it here. And this will go ahead and get the process started. What the chunking process looks like is that if I go ahead and specify that I want to have 100 kilobit chunks, and I get a request next message here, and I reply back with a message that when we've fully serialized it is 400 kilobits in length, we're going to go ahead and store 4 separate 100 kilobit chunks. And the first chunk will get delivered over the network. Next chunk might get delivered and so on and so forth. Now, by the way, all the previous chunks are actually stored in both places while this is happening. We have and not to mention the original message is also stored inside the producer controller. So we're actually still keeping all this stuff in memory. The producer controller will basically send all these sequence messages over the network. Once the consumer controller knows it's gathered all of the chunks it needs to do its work, it'll go ahead and deserialize that. It'll go ahead and reconstitute that original message and deliver it to the actor, who will then confirm it, and we'll get a request message back, and we'll mark all of the chunks as delivered and purge them from memory at that standpoint. And then we'll request the next message from the producer. So this chunking system is very good at being able to go ahead and take messages that might normally struggle to get serialized over the wire. We can break them apart into smaller bits, interleave them with other messages, and then stream them over the network without having an adverse effect on our reliability inside our network. So that's what's going on here with this sort of chunk reassembly. Now we'll go ahead and do a little example here. So let me pull up let's see. This is our SQL sharding example, which is part of the Akka.NET code samples repository in the Petabridge GitHub repo. And I basically have 2 different processes here. Let me go ahead and start them up real quick. Start up the web app. And let me just see my index actor here. Let me grab this. I think I have chunking turned off right now. Yes, I do. Okay, cool. Let me start this up. And I'll go ahead and start a second instance of this process as well. Okay, looks like everything should be up and running. Let me go to my web app and grab this URL. Okay, so I'm going to pull this over. So this is, if I go and take a look at our web UI, this is, grab this, our Akka.NET code samples repository, and I'm running using this branch right now, and I'm using the Akka.NET nightlies to go ahead and do chunking. So like I mentioned, we will release a beta version of this relatively soon. So here I have a set of, roughly 60 various products that I've entered here. And I can go ahead and dig through any of these. Well, one of the issues that I have had in the past with this demo app is that when I use the automated sort of, let's say, entity creation mode for this, where I can go ahead and dynamically populate like 21,000 entities and try to get a list of all 21,000 of them all at once, usually that message is larger than the default message frame size, and as a result, won't get delivered. So one of the things I've done here is I've instituted Akka.Reliable.Delivery behind the scenes. So let's take a look at what I did inside my little web controller right here. This is the page that's basically displaying all those products. So this little product data tuple right here just has sort of a product ID, product name, and the current price as a decimal. And I have a little component that I pass in here, this little iProducts resolver. This products resolver, when I call fetch all products async, will return, if I take a look here, a little fetch all products response, and I'll order those products by descending order of price and render them on screen as part of my view model. Pretty simple stuff. Well, this fetch all products component is going to use Akka.Hosting's dependency injection system to introduce my fetch all products consumer actor into this application here. This is an actor that I'm going to ask. I'm going to send this actor a fetch all products query. I'm going to get a fetch all products response back. All right, so how does that work? Well, this actor this is a singleton actor. There exists exactly one of these inside each of my web application processes. And this is just an untyped actor with a stash and with timers. And what's going to happen is I'm going to take this product index actor. This is a cluster singleton proxy. This is going to point to the product index actor that there's only one of them that runs inside my oldest SQL sharding.host process right now. And that actor, which is right here, this actor, this product index actor, uses, if I scroll down real quick, in fact, let me make my font just a little bit bigger. This actor uses Akka.Persistence.Query to basically get a list of all product IDs. And then for each one of these product IDs we find, we go ahead and query that entity actor for a little bit of data. And we use that to basically maintain, if I scroll up here, this dictionary of product IDs. And this is the information we send back whenever we receive a fetch all products query. This one right here. Okay, so I rewrote this to use Akka.Delivery in order to make it a little bit more robust. So here's what I did. This actor, my fetch all products consumer, is going to create a consumer controller right here. So I'm just going to use the default settings. I'm going to go ahead and call consumer controller.create. I'm going to pass in a reference either to the actor system or to my current actor context. I'm going to pass in basically, this is an option type in Akka.net. I'm going to say we're going to use an empty option here. We don't have a producer controller that we have access to right now. Then I'm going to pass in my settings. And I'm just going to call actor of right here. And then I'm going to tell this consumer controller actor to start delivering messages to me. All right, pretty straightforward so far. Every time I receive a fetch all products message, I'm going to go ahead and tell, whoops, I think I did something here. I'm going to go ahead and tell the product index proxy actor that I want to fetch all products right now. And I'm going to include a reference to my little consumer controller actor right here. And I'm also going to include a reference to my little unique producer ID. This is the sort of a little GUID that I generate on the fly right here for this actor. All right. So I'm basically going to pass those two pieces of data back to the server. And I'm going to shift my behavior to waiting for response. And I'm going to take the little temporary ask actor who sent me this fetch all products message, and I'm going to stick it as a little closure in this method down here. And then I'm going to wait for the consumer controller to go ahead and deliver this fetch all products message to me right here, this fetch all products protocol. It's the type of protocol we're using. And as long as this payload is a fetch all products response, I'll go ahead and deliver this to the original requester. And I'll tell the consumer controller that I confirm receipt of this message, and then I'll move on. And then any additional requests that I get while I'm in the state, I'll go ahead and stash it. And then when I have received my delivery message right here, I'll unstash that message and go back to being active again right here. So this is a little bit of infrastructure I set up on the consumer side in order to do reliable delivery of messages. Let's see what the producer side looks like. On the producer side, because this is a cluster singleton, and I might have multiple consumer controllers on different nodes in the cluster all try to contact me, I made a little dictionary right here where I have my producer ID, I have a reference to my producer controller, and then a little Boolean that indicates whether or not there's demand for on this particular connection at a given point in time. Again, this is a pretty simple little data structure. When I receive a fetch all products request, I have a little method down here, receive fetch products, where I pass in this request here and I include an attempt number. I basically check to see, do I already have a producer controller that corresponds to this node? If I do, then I check to see if we have demand. And if I do, I go ahead and I just send a fetch all products response back. And I basically going to take all of my values that I have here and turn them into a list. This will get serialized and optionally chunked and transmitted over the wire. And then I go ahead and signal that we have no demand for now. And I go ahead and basically just cancel. If we had a timer active, I cancel it. Otherwise, if there is no demand, so meaning that I don't have the ability to answer this request right now because there might be another request in flight already, I go ahead and I schedule a retry 1 second from now. Now, in the event that I don't have a producer controller for that node yet, I go ahead and I start one by calling this create producer controller method, add that to my dictionary, and then I go ahead and I retry the request down here. And let's take a look at this method, create producer controller. We already kind of saw this on screen earlier. I create my producer controller settings. If I want to turn on message chunking, I can do that right here. I pass in the same message protocol we had before, and I register this requester as the consumer, and I register myself as the producer. And then the only other message I really need to handle, if I scroll up here, is I wait until I receive this request next message right here, in which case I just go ahead and signal that we are ready to go ahead and produce this message right now. And so I go ahead and just flip that bit to true. And then when that message gets retried down here, assuming that there's capacity available, I can go ahead and deliver it. In fact, if I go here and I hit reload, I'm actually re-requesting this data every single time from that node. Moreover, if I go ahead and kick the old node from out of the cluster, let's do that real quick. I'm going to go ahead and kill, I think it's this process here. Go ahead and shut that one down. So I'll have that node leave the process. Let me take a look at the run window here. So it looks like this node left the cluster. Looks like that member got removed and our cluster singleton is moved. Okay, so that should all work. I'll go ahead and reload the screen here. And voila, everything went through as normal again, even though I completely replaced the producer controller. So one of the things that's pretty cool about this technology, the reliable delivery system, is that the producer and consumer controller can basically restart independently from each other, and that's not going to really interfere with the reliable message delivery. So this is a really kind of simple request response system I set up on top of the producer and consumer controller stuff. And I really set this up because I've had issues with head of line blocking on this code sample before. For most user applications that are simple request response ones like this, you probably don't need to bother implementing the producer and consumer controller. I just did it because message chunking actually does solve a real bug for me here. That's why I did it. Now, the next thing we'll take a look at is the durable producer flow real quickly. If you want to persist these messages so you can survive a full process restart, what would that look like? Well, in this case, the way that works is we would go ahead and pass in an additional configuration value into the constructor of the producer controller right here. Would pass in props for what's called the event source durable queue. And the way this works is that when I receive this request next button here, this request next message, I can reply back. Instead of replying back with just a message of type T, I can reply back with a message with confirmation of type T. And when that happens, our message might get persisted to a durable queue if we have one enabled. And once we've confirmed that this message has been persisted to the durable queue, I'll get a reply back that has a sequence number that corresponds to this message. That way I know for sure my message has been queued and is not going to get lost at this point. The durable queue has a copy of that record and it's going to stay there until that message gets successfully acknowledged. And so I modified my configuration code a little bit just to kind of show you what the durable queue looks like. Let me grab my pen here. This is literally the only additional piece of code and this bit right here that I need to basically make the producer controller durable. It's like one new line of code is all that we needed to do in order to do that. So as long as basically this type and this type match, we're good to go. We can go ahead and make sure that everything will work. Now, in the event that the durable queue fails, let's say it chokes while trying to serialize a message, what that'll do is it'll cause the producer controller to restart, and it'll go and basically that'll force the durable queue to get destroyed and recreated again. And by the way, that also won't have a negative impact on message delivery. The only way that would be if the message wasn't persisted to the durable queue. Then we'll immediately turn around and say request next to the producer, and the producer will have to redeliver that message again. That's what the message with confirmation is for right here, is that if you really want to make sure the message was queued up, you would send this probably using the ask keyword. In fact, if I take a look at our code sample real quick, let me grab that. If I go to my producer down here, when I get this request next message, if I go to next dot, let me go ahead and shut this all down real quick so I can get some proper IntelliSense. Give me just a second here. All right, there we go. What is this mad about? Yep, there we go. That should be fixed. Let me go to where the request next was. This is the wrong actor. Let's see, request next. There we go. If I go to next dot, there's actually an ask next to, which returns a task you can await on for this. So you can go ahead and just pass in your message right here and a cancellation token. And if you do that, you'll get a task that you can await on. And that task will complete once the message has been properly saved in the durable queue. So we try to make it really easy to make sure this message will 100% for sure get delivered. Let's see. Now, a couple of important notes about how the system functions so far. The first is that the producer and consumer controller can survive with the other restarting. The one thing that you might notice is that the sequence number will reset back to 1 if the producer controller restarts, unless we're using the durable queue. If we're using the durable queue, it'll reset to whatever the highest value was that we pulled out of the durable queue. If the producer controller is durable, we're going to resume by delivering the oldest unconfirmed message. So this is preservation of message order. We're going to begin with first in, first out order and try to deliver that over the wire. Now, the one area where you can possibly get a duplicate, and this is an edge case of an edge case, is that if the message was confirmed by the consumer in flight as the producer controller restarting, you'll get a duplicate. The reason why that is the old producer controller died before the consumer controller could have basically acknowledged that message. Like I said, that's an edge case of an edge case. Very unlikely to happen in most scenarios, but that is something you might want to be prepared for. We are looking at possibly fixing that on our end. That actually should be possible to do through the consumer controller, but we haven't implemented it yet. Couple of other notes. If the producer dies, nothing happens. So the producer dies, the producer controller is just going to wait for another one to get registered. So as long as the producer actor resends a start message back to the producer controller, then we're all in good shape again when that happens. And when I say die, I don't mean restarts. I mean the actor ref is actually terminated. And then a brand new one gets created, and that one starts talking to the producer controller. So the producer controller doesn't really care if the producer's dead or not. It doesn't death watch it. It doesn't monitor it at all. The only actor that actually gets monitored by the producer controller, period, is actually going to be the durable queue. If the producer sends a message to the producer controller when there's no demand, the producer controller will crash and restart. This basically means don't blindly fire messages at the producer controller. Listen for those request next messages. They're actually important and they do mean something. So you want to listen for those messages and let them dictate the pace at which you can message the producer controller. Finally, if the consumer dies, the actor that's ultimately responsible for processing this message, if the consumer dies, the consumer controller dies. Basically, if the consumer's dead, then none of the delivery state matters anymore, and the consumer controller is going to kill itself. And if those actors restart and they resync with the producer controller, the producer controller will begin by redelivering all the unacknowledged messages. So again, nothing of value will get lost if this happens because the producer controller is the one who's in the driver's seat for all the state here. So that's typically how it's going to look. The last thing we'll touch on as part of our show and tell presentation is I'm very excited about using this feature in one of our products that we're working on right now, which is the ability to go ahead and get a reliable delivery across cluster sharding. So one of the primary use cases we're interested in this feature for is what happens when a shard gets rebalanced. Today, we have built-in buffering where once we know the rebalance is happening, we're going to go ahead and buffer message traffic between the rest of the cluster and those entities. But in a really high throughput system, that still means some messages are gonna die in transit because they were sent basically between those actors shutting down and the system knowing that they were shutting down. So there's a gap where you can lose messages here. This system effectively closes that gap and makes sure that any message that was queued up by a producer will be redelivered in the original order it was queued up for that entity if you allow it. And by say if you allow, I mean by if you use this code. So this is the Akka.Cluster.Sharding.Delivery functionality, which uses a sharding producer controller. And here's the other cool bit. I used a couple of different producer controllers for working with consumer controllers in my last code sample. You typically only need a single sharding producer controller per actor system per region. So if you have 2 shard regions inside your cluster, you probably want to use 2 sharding producer controllers, one for each. In fact, you would have to actually. So that's typically how it works. You don't need a bunch of sharding producer controllers. One per actor system is enough. Sorry, one per actor system per shard region is enough. Next, the sharding producer controller will automatically create a producer controller per entity. Every entity's delivery state is tracked independently from every other entity. And on top of that, once entities haven't received message from this node in a while, we'll gradually begin killing off their producer controllers in order to free memory back up for your system. Optionally, the system can be made durable, and we're very efficient about how we do it. We use one durable queue for storing the delivery state for the entire actor system for one sharding producer controller. So that means that we're not filling up your journal with a ton of crap. We're very conservative about it in this instance. So the sharding producer controller is pretty good there. The one thing the sharding producer controller does not support is chunking. That is something that we would need to do they don't support that on the JVM either. That is something we need to do a fairly significant revision on in order to support that. But that's kind of not in scope for right now. I think most users will probably be okay without it. And we'll have our code sample I just made will actually show you how to set up messaging over Akka.Cluster that supports chunking without necessarily relying on the sharding system to do that. Finally, this should say sharding consumer controller. Sorry, it's a bit of a mistake on my part. We have a sharding consumer controller that actually is the parent that is spawned by the shard region in our application. And every time one of these starts up, we go ahead and create a brand new consumer controller for every single one of the producer controllers that contacts that entity. So we're able to go ahead and use the actor system's ability to inexpensively spawn actors to make it possible for us to correlate all this activity from all these different senders to all these different receivers. And this is actually less work to set up than the normal producer and consumer controller. The reason being is that you don't have to worry about registration in the system. The producer controller and the consumer controller will automatically be registered with each other by virtue of the sharding system. So what this looks like in practice is we have the sharding producer controller and we have our shard region. The shard region is going to create the sharding consumer controller, and that in turn is going to start your consumer actor here. When we start producing messages, there is one kind of important caveat. When we're producing messages for the sharding producer controller, you have to use a type that is built into Akka.net called a shard envelope. This basically allows us to take your type and the entity ID and allows us to go ahead and wrap those together and securely transmit them back to the shard region here. We're going to produce so one of the things I'm working on today is our documentation for this system here, and this will be clearly outlined there. You need to message the sharding producer controller with the shard envelope. If you do not do that, it will drop your message and it will not deliver it, and you will see an error show up in your log. So you've been warned. Where for every single entity that we detect in one of these shard envelopes, we're going to create a producer controller, and we're going to take the messages that were in your shard envelopes and rewrap them inside a sequence message and deliver it to that shard region. The shard region will in turn deliver that sequence message to a sharding consumer controller. who will in turn spawn a consumer controller for that producer, deliver the sequence message, who will then turn deliver that to the consumer, who will in turn confirm it, and basically kind of run the exact same process that we did for producer and consumer controllers before. This request next message you get when you're working with a sharding producer controller is a little bit different than when you're working with an individual producer controller, because it'll go ahead and tell you, here's what the entire state of all the entities we're working with looks like at any given time. And it'll go ahead and tell you which entities have demand right now, which ones do not, and also tell you the buffer sizes for all the individual entities you're looking at. So you get a full picture of what your system's traffic looks like every time you get a request next message. That is actually an extremely useful form of telemetry we've never had before. So that's something that we're going to be taking a look at in our code sample here. Let me pull that up real quick. This code sample is part of the Akka.net project. Let me go and close my tabs here. And it is in the cluster sharding shopping cart system right here. And I'll go ahead and pull up our actors. And let me just make sure I am in the right folder. Let me grab my console here. All right, there we go. I'll hit pull. And let's see. It is start.command as I need to run. Okay, cool. I'll do that in just a second. So what do we have here? Well, if we take a look at our program.cs, let me close that real quick. We start the sharding system, and depending on what role we're in, we'll do something a little different. I'll start a shard region proxy if we're in a front-end role. And if we're in a back-end role, I'll start my shard region. So we have two different role types we can instantiate with this one process here. If I'm starting my shard region right here, get a load of this. We have this method that's built into Akka.Cluster.Sharding called an entity props factory. One of the things we're going to do a little differently is rather than just returning our customer actor, we're going to wrap that customer actor inside a sharding consumer controller. Now we're going to kind of nest the actor types here. We're going to say this sharding consumer controller will process a message of type I customer command. And we'll go ahead and basically create down here we'll pass in basically a little function that's going to create the props for our customer actor. And this C right here is an actor reference that refers back to the sharding consumer controller actor itself. So we'll pass that into here. And then we'll pass in our settings for the sharding consumer controller as well. Let's take a look at what our customer actor looks like. This is our consumer. This actor, when it first starts, will go ahead and tell the consumer controller actor, which we take a reference to in our constructor. We'll tell this consumer controller actor that we want to register ourselves for message production. This is going to start the sharding consumer controller's ability to deliver messages to this actor. And then every time we get a delivery message, we're going to go ahead and do a little bit of processing here, and we'll confirm that message back to the consumer controller in order to keep the delivery state going. So even though this consumer controller is actually handling a fairly sophisticated set of messaging for the consumer actor, this is very light touch from a code standpoint. It just requires a little bit of configuration changes, and that's all that we need. On the message production side, if I go here where we start our shard region proxy, I'm going to go to our produce messages function right here. So I pass in a reference to my shard region proxy, and I'm going to create a little producer ID right here. So this has to be globally unique. You want the producer IDs to be unique. So what I'm doing here is I'm just taking a string and I'm hashing our address and combining those together to form a globally unique producer ID. Down here, I'm going to go ahead and create a brand new sharding producer controller. I pass in a producer ID, a reference to our shard region proxy. I'm not going to use a durable queue at this time because this sample doesn't use Akka.Persistence. And then I pass in my settings. And then I'm going to pass in just the name of this actor. And then what I'm going to do is I'm going to create a little producer actor right here. And I'm going to register that as with the sharding producer controller down below. Then we take a look at our producer actor right here. This producer actor begins in an idle state. Every time I get a sharding producer controller.request next, I go ahead and I become active and I set the send next to as a little property here. And then in my active state, let me see if I can find this. In my active state, when I receive a produce command, I go ahead and I pick a random customer, pick a random item, queue it as a sharding envelope, and then deliver it. And I wait for more demand to come in. Otherwise, down here, if I get another request next while I'm in this state, I might go ahead and just update my send next to. But either way, I'm going to go ahead and wait for this request next to come in before I deliver. If I really want to deliver quickly, I can do this. Let's see, I think this needs link, which is I can go ahead and pick entities that have demand available to them right now and immediately deliver something if I want to. So let's try running the sample real quick and see how well it goes. Let's see. I think it's start.command. Let's go and build a little Docker image real quick. And basically, I think he uses Docker Compose to deploy 2 front ends and 2 back ends. All right, there we go. Okay, looks like the system's up and running and great. We're reliably delivering messages over the network now. That all looks pretty well and good. And if I let this run for a little while, you'd go ahead and see all of our entity actors, which are, if I go to our producer, our entity actors are named after these Star Wars characters, and these are the messages we can send them. They'll go ahead and fill up with all sorts of messages here. And the total amount of memory being used is pretty small for each of these processes here. So it's not going to overly burden your system. It's not a huge amount of work from a messaging standpoint. Akka handles the serialization of all these envelopes for you, so that's taken care of too. All you've really got to do to from a design standpoint is you really want to use something like a marker interface for the messages in your domain. Group all of your messages underneath that, and have that be what gets handled by your your consumer and producer actors on the other side. So that's what I've got for you today on Akka.Delivery. We're going to do an additional YouTube video on this. And then on top of that, we're going to produce some written documentation and ship a beta version of this probably this week. So you can start playing with it. Gregorius, do you have any questions about any of this before I take some questions from the audience?
Nope. It seems pretty clear to me.
All right, good. Okay, any questions from anyone who's attended today? I'll go ahead and give them a couple minutes. Well, a couple seconds anyway. Nope. Okay, well, thank you very much for your time today. And I realized we went about 15 minutes longer than we normally do. Thank you very much for sticking with us. I hope you appreciated what we showed here. We'll be doing a separate YouTube video and some more documentation on it. But in the meantime, thank you very much. We look forward to seeing what you guys do with this feature. So thanks for your time today, and we'll go ahead and catch you next time. Thank you.